Hello everyone, this is Priyanshu Choubey, Assistant Professor of Suresh Gandhi University. Today we will talk about the minerals, what is minerals and identification of minerals. We already discussed about it. And next slide we will discuss about dioctahedral minerals of colonite groups. So let's see what is it. Dioctahedral minerals of colonite groups each of three minerals connected in this group colonite, dictite, and nerkalite on a tetrahedral sheet is linked by its apical oxygen to an octahedral sheet connecting two thirds of its octahedral sites occupied by the trivalent aluminium ions. The linking oxygen to belong to both tetrahedral or octahedral seed. Other atoms in this plane are the hydroxyl groups which belongs to the octahedral sheet. These hydroxyl groups are called the inner hydroxyl group and called groups and are located vertically above a hexagonal activity cavity. Those hydroxyl groups placed at the outer surface of the octahedral sheet are called the outer hydroxyl group. The unit cell of calonite in ZY or CB plane. Unit cell is that a smallest three-dimensional section of minerals which repeated in all the three dimension as along the z-axis. C dimension of the cell started with the plane of outer hydroxyl group of the octahedral sheet having a six hydroxyl groups followed by octahedral aluminum plane, four oxygen and two hydroxyl plane, tetrahedral four silicon plane, and outer six oxygen plane, which makes a hydrogen bonding with the hydroxyl plane of the octahedral sheet of the next kalinite layers unit. This distance from the hydroxyl plane of one unit to the corresponding OH plane's hydroxyl plane is the repeat distance along the C-axis and is called the C-axis spacing of the mineral. In the plane of outer oxygen, more than six oxygen are here. The oxygen with cut bond share only half with the oxygen in the unit cell. The other half is shared with the oxygen with a silicon of other unit cell. There are six such half shared oxygen and three full shared oxygen shown here in the containing a total six oxygen. If we calculate the total positive charge of the cations and the total negative charge of the ions in the unit cell, so like a cation, 4 aluminium is equal 4 into 3 is totally 12 cations and silicon 4 silicon, so 4 into 4 16 silicon here. And anions 6 OH is equal minus 6 into 6, so minus 6 hydroxyl and 4 oxygen plus 2 OH minus 2 into 4 minus 1 into 2 minus 10, and 6 oxygen is equal to minus 2 into 6 is equal to minus 12. So total cations 12, 28 and total anions minus 28. So the net charge is zero and thus the structure is neutral. And the unit cell formula is aluminium 4, silicon 4, aluminium 4, 10 oxygen, O chat, confirming to the phyllosilicates formula of silicon 2 and oxygen 5 for the 1 ratio 1 trioctahedral serpentine, the ideal chemical composition of magnesium 6, silicon 4, oxygen 10, and hydroxide 8. Serpentine contains only divalent cations in the octahedral suite. Layer silicates minerals, the structure of 2 ratio 1 layer structure consists of central octahedral sheets joined through oxygen atoms. Two tetrahedral sheets above the below. These oxygen atoms are common to octahedral sheet and tetrahedral sheet as its apical oxygen of the tetrahedral. Pyrophilolite and the talc are the regarded as the prototype of all 2 ratio 1 minerals in dioctahedral and trioctahedral groups respectively. Pyrophyllite, this structure formula as a pyrophylite is aluminium 4 and oxygen 8 and silicon 8 and oxygen 20 OH4. The pain-wise atomic distribution in the unit cell has been total positive and total negative charge in the unit cell due to cation and anions are equal to 44, making the structure to be ideal electroneutral. Because of its neutral structure, there are no interlayer cations, nor is there any tendency for the minerals to self by intra swelled by cations of the water or organic liquids between the layers. Pyrophilites is relatively uncommon minerals formed by the hydrothermal alternation of feldspar and is rarely found in the soil. Talc, it is a octahedral po- prototype of ideal 2 ratio 1 minerals of the same structure as that of the pyrophyllite, with the difference that is talc all the octahedral sites are uh, filled up by a divalent magnesium ions, and structure formula are magnesium 6, oxygen 8, no, oxygen 20, or OH4. Neutral talc show as a wider range of a composition and may contain a ferrous iron. In some cases, a nickel substitute for a magnesium in the octahedral sheet, but as a whole, the mineral is electroneutral and there are neither interlayer cation nor there is any intercalculation with the organic liquid or water sense. In talc, octahedral sheet is a bigger in B dimension because of a layer. Divalent ions fill up all the octahedral sheets. There is an almost exact match between a regular tetrahedral sheet and the octahedral sheet. The tetrahedral rotation is very small, is that only a 3.4 degree. There are no interlayer cations and in either a pyropholites or a talc, nor is there are any tendency for the minerals to swell by interaction of water and organic liquids between the layer. In both the case, the interlayer bonding is through weak van der Waals force to that one layer and can side over the other with the little force. These materials can thus be used as a solid lubricant and due to inert nature, this find use as the filler materials. Basic skeleton of all the 2 ratio 1 minerals is either same as a pyrophyllite in case of the dioctahedral type as talc is a case of a trioctahedral type. In soil, this mineral don't confirm this ideal structure. A lot of substitution in minerals latex uh, occur, resulting in variety of minerals. Minerals arising out of this transformation among each other with respected to their like a layer change due to isomorphous substitution, location of a layer change, charge, and types of substituting cations. So different 2 ratio 1 minerals are different amount and location of layer charge. So mineral groups like dioctahedral minerals and layer charge equivalent unit cell range and the name of the end member minerals, octahedral substitution and tetrahedral substitution interlayer. So dioctahedral minerals like a pyrophyllite layer charge is 0 to 0.4. Octahedral substitution pyrophilites and tetrahedral substitution pyrophilites, no iron or sheet. Semicitide 0.4 to 1.0. Montmoronite octahedral and tetrahedral bedite, any hydride cation. Vermiculites 1.2 to 1.8. Vermiculites hydrated magnesium. Mica 1.8 to 0.2. Saldonite moscovita under hydride potassium. Trioctahedral minerals talc 0.04 and talc non-iron ore sheet. Semicides 0.4 to 1.2. Hectororite and spironite, anhydride cation, and vermiculites 1. 2 to 1.8 vermiculite, vermicular hydride, magnesium, and mica 1.8 to 0.8 tanonite and biotite, anhydride potassium. Mica group of minerals having a 2 ratio 1 layers structure like pyropholites and the talc with a maximum layer charge due to isomorphous substitution, namely 2 equivalent per unit cell of a 4 unit in the rare mica. In dioctahedral mica such as the Moscovita, isomorphous substitution take place in the tetrahedral sheet. One out of four silicon is a substitution via aluminium. Thus, producing two equivalent negative charge in the unit cell in the mica. The negatively layer charged is balanced by a potassium ion in the interlayer position. Thus, is the ideal unit cell formula is a K2 silicon 6 aluminium 6 aluminum oxygen 20 and OH4. Because of very high layer charge, the electrostatic energy of a two adjacent layer for the potassium ions in the interlayer is very high. To reduce this energy, the two layers come close to each other, taking potassium ions partially inside the diatrigonal cavity by scrubbing the water of hydrogen of potassium ion, which is weakly hydrated. This is called a potassium fixation. Unhydrated diameter of a potassium to 0.66 angstrom, which is almost same as that ditrigonal cavity. Favor this fixation process, thus the C-axis spacing D001 of Moscow beta is a 10 angstrom. An ion having a high ionic potential is at a high charge size ratio becomes strongly hydrated with a high hydration energy, which is very difficult to scrap its hydration layer. Those ions such as sodium, calcium, magnesium cannot be fixed in the interlayer of mica because of their high hydration energy and also due to their smaller hydration smaller unhydrated size than the ditrigonal cavity. Muscovita is a primary mineral occurring in a different rocks. One of its weathering products is a elite, which occur extensively in the soil. Its structure resembles that of a muscovita, but contain less potassium. More water has less size, less than 2 and less layer of charge due to a weathering. Although mica and elites have a very high layer charge, interlayer potassium neutralize this charge. These minerals have less cation exchange capacity. Because interlayer potassium cannot be exchanged easily with other hydride cations in solution, thus potassium is held very tenacious tenaciously in the interlayer potassium. So vermiculites group uh, dioctahedral vermiculites has a total 1.8 equivalent layer charge. In the tetrahedral sheets, this charge is neutralized by a zero point 0.9 moles of a hydride, magnesium 1.8 equivalent, with the two layers of water in the interlayer position. Not more than two water molecules layer can be present in the interlayer because of a high electrostatic attraction due to high layer charge. Although its layer charge is more than mica, all of its layer charge is expressed as a cation exchange capacity. This interlayer magnesium can be exchanged with the other cations. Thus, this is the clay minerals having a maximum cation exchange capacity. Montmorillonite group. Montmorillonite group is a member of Semetites group of minerals which with formula uh, calcium 0.5, sodium 0.2, silicon 8, aluminum 2.8, and magnesium 1.2, oxygen 20, and hydride 4. All of these, the layer of charge at 1.2 equivalent per unit cell appears of as a cation exchange capacity and neutralized by a zero point 0.4 moles, 1.2 equivalent calcium, and zero point 0.2 moles of sodium, and exchangeable cations present in the interlayer in the hydride form. The C-axis spacing depends on moisture because of low layer charge. They can absorb a moisture in the interlayer and expand to a very high spacing, particularly with sodium. Two ratio, one ratio one type chloride group. Structure of ditrichloride in this group. The interlayer is occupied by the octahedral Versite seats in this interlayer sheet positively charged developed by a substituting lower valent cations, say magnesium, by high valent cations, say aluminum, which then neutralize negative charge in the tetrahedral sheets or octahedral sheet thus get attached together. Thus, this minerals has a capacity pa, pa, this mineral has a practically no cation exchange capacity. Mixed layer minerals and enter certified minerals. In this group, minerals are one particles contains layer of more than one types of layer stuck together along three-dimensional as this stacking may be a regular or random or accordingly these are called a regular or random interstratified minerals respectively. Hydroxide enter layer minerals during pedogenesis synthesis of the minerals of clay minerals and soil. Hydroxide first aluminum ions due to their positively charge enter in the interlayer of vermiculites or montmorillonite and the polymerase thereon gradually filling the interlayer position. If the interlayer is completely filled in then a pathogenic chloride is formed. But if the interlayer is not filled completely, then the mineral found are called a hydroxyl interlayer. Vermiculites and hydroxyl interlayered morillonite. These minerals depict C excess spacing of more than a 10 angstrom but less than 14 angstrom. Amorphous soil constituents are those materials which lack long range order in the one or all the three-dimensional produce broad or no X-rays different X-rays diffraction peaks. These materials process large specific surface area and more relatively than the crystalline minerals. They develop a variable charge on their surface. The presence of these materials markedly affect on the physical, chemical, and biological properties of the soil. Uh, Paracrystalline minerals are those having a long range order, are two-dimensional only with or without differ. Allophane, these are a paracrystalline aluminosilicate mineral which defect produce a no X-ray diffraction effect. Allophane are very small spherical nanoparticles having a diameter 3.5 nm. Um, Presumably made up of one aluminium octahedral and one silicon aluminum tetrahedral sheet. Silicon aluminum ratio is more than one. Amo Amygdalite. These are a paracrystalline aminosilicates minerals without a defect produce a broad X-rays difference peak. Amygdalite are in the form of a very thin 100,000 nm along tubes having a diameter of about a 2 nm made up of the one gibbsite sheet covered in the form of the tube. The orthosilicates group attached to the inside of the tube silica aluminum ratio is 1. Aluman and imogolite occurs the pathogenic due to a soil process. Product not only in the andosol salts derived from the volcanic ash but also is those derived from the massive basalt. Offline silicates, these are non-crystalline, circular or the epic- elliptical plates or a sphere of 100 to 1000 nm size. These are three-dimensional tectosilicates with only a short range order. Ferrihydrite, it's consists of a spherical with a diameter of 3 to 10 nm and has a hematite-like structure where oxygen is replaced by a hydrogen group. So oxides and hydroxide, oxygen oxides and hydroxides of aluminum and iron occur dominantly in soil. Independent crystalline minerals or as amorphous coating on other minerals such as layer silicates. When these minerals are formed as a fresh precipitates, these are amorphous with a small particle and large specific surface are more solubility and reactivity as exhibited by the adsorption of other ions and molecules on their surface. The common feature of these minerals that a cation Aluminium, iron, and manganese remain in octahedral coordination of a six-fold coordination surrounded by a six group as at the sixth corner of and the imaginary regular octahedron with oxygen, hydroxide, and water or a several combination of these groups. Some of these compounds having the same chemical formula, but these different types of packing, such as the cubic close packing of hexagonal close packing, she earlier section lead to the different types of symmetry and crystal system. These types of minerals having a same chemical formula, different structure of packing or three-dimensional are called polymorphous, and this phenomena is called polymorphism. Aluminum hydroxides and oxyhydroxides. Aluminum hydroxide, aluminum OH3 gibbside is most commonly found in soil. And the other two uncommon polymorphs are the barite and Nostantine. Aluminium oxyhydroxide, biothymite, and dispores or two polymorphs have a minor occurrence in the soil than gibbsite. Aluminium oxide, the anhydrous aluminum oxide, a high temperature product, is present only minor components of igneous and metamorphic rocks. So here completed all about dioctahedral minerals of kaolinite groups, layers of silicate minerals, and all these are principle of structure group and mica groups, different 2 ratio 1 minerals and different amount and location of layer charge, and vermiculites groups and montmorillonite groups and types chloride groups and mixed layer minerals and intersatisfied minerals. Hydroxy interlayer minerals and amorphous soil constitutes oxides and oxides and aluminium hydroxides and oxyhydroxides groups. Mm, thank you.